So as I said, in our class, we have total of 8 different labs. Every lab is trying to test the material under specific load, or maybe test one specific property of the material. Our first property for our first lab called hardness, and the objective of this lab is to determine the relative hardness of the material using a machine. And this machine, actually, we have two. You can see on my screen, the two machines are in the slide on my machine. Two machines are on my slide. The one on the left, as you can see the name, it's called Rockwell, and the one on the right is called Brinell. And before I start showing you this lab, it's just like how do we test the hardness of one material is by pressing very hard on the surface of the material. Just like when you push your, try to push your finger into your cheeks, okay? So kind of pushing into your cheek, so it will create some sort of deformation. And that's exactly what we do here. Let me show you first, before we go into the details of individual tests, let me show you what happens if you drive with a high pressure on the surface of one specimen, okay? So let me get my pointer, and here we go. So on the right picture, you can see as soon as you try to push very hard with high pressure on the surface of the metal, this is what you get. You get something like, call it mark, call it indentation, call it deformation. However, at the end of the day, this is what we get, okay? We get a mark. Now, I hope you understand that the size of the mark, it tells you how hard or how soft the material. The bigger the mark, it means the material is so soft. And the smaller the mark, the material is hard. Does this make sense for you? Excellent. So that's exactly what we do, is we apply high pressure on the surface of the metal. Then once we are done, we get this mark, and we simply somehow measure the size of the mark. The size of the mark will tell us, inform us about the hardness of the material. Now let's go into the specific details of each individual test. So as I said, we have two machines on the right here that's called Brinell. On the left here, it's called Rockwell, and they work almost the same way, almost same way. So I'm going to start here with this one first, called Brinell machine. So in Brinell machine, you place your specimen right here, and you apply a pressure, high pressure, and this gauge here will tell you the amount of force. And with this handle, you can control the force. Now, Mr. Brinell said, if you want to find Brinell hardness number, which is PHN, you have to use this equation right here, which is you divide the applied force in kilogram, you divide by some sort of area, okay, some sort of area. Now, in this equation here, which allows you to find the PHN, which is a representative of hardness of the material, how many parameters you see on the right side? I guess 3. Those 3 parameters are right here. Number 1 is the load in kilogram. So we take our load in kilogram, that's the P. Number 2 is we use an indentor, and I'm going to show you the indentor right now. I think it's right here. So just take a look here, and that's how the indentor look like. It's a metal ball of diameter of 10 millimeter, and that's constant, huh? So this number is constant. D uppercase, this D right here, it's always 10. Now the last element in the equation is lowercase d. And so what is lowercase d? Let's go back to this picture right here. Simply the lowercase d is the diameter of the dent or the mark. We don't measure it using like a ruler or scale. However, we want to measure this diameter very precisely, and that's why we use this simple tool. So this simple tool here, very simple. It's just a scope, like surveying scope, and you can see there is some light. When you turn the light, that's what you see, huh? So there will be light. You can turn on the lights. When you look through the scope, that's what you see. You see the dent. You also have a scale, and this scale allows you to measure the dent very precisely. Like you can say, for example, my D is equal to 4.5 mil. So you can measure to a fraction of a millimeter using this scope. So again, very simple. We use the diameter of the dent, but we don't use it using a ruler. We use this little simple device to measure the size of the dent. Once you have the size, then you can go back to this equation. You just use the load that you apply. The indentor, the diameter, uppercase D is always 10 millimeter. And finally, this is the size of the dent that you measure using this scope. Now, and then finally, what you get is you get Brinell hardness number, and this number, as I said, it represents the hardness of the material.
Sorry
Think
to
about the
interrupt you,
units.
Connor. I already double checked the PDF on a D2L and the formula is not there. I'm not sure if you can is it just for me or everyone can see this formula?
So you
The
cannot see this
printout
one.
machine, yeah, those formula, it doesn't appear on my PDF.
Oh my
So
God. Sometimes here's the problem. Sometimes when you print a PDF, the PDF printer doesn't like. So you know what? My recommendation for you is I'm gonna show you the formula because looks like my PDF printer is not working perfectly. So please take your time right now and copy this formula to your notes. It is simply the load, and just I'm gonna zoom in here and please copy it, okay? And make sure that you understand the math. Huh? So the pi d over 2 multiplied by a bracket. Within this bracket is d minus another bracket, d square root of d square minus lowercase d square. Okay, so take your time, copy this formula. And again, after the class, I will just try it one more time. But sometimes I know that sometimes the PDF printer is not very friendly with some equations. Okay, so just copy it for your notes. And when you're done, please let me know.
Tar, can I have a next page as well? The Brinell machine. Uh, the next page after this. Yeah, thank you.
Just please let me know when you're done, okay?
All good.
Excellent, thank you. So
Yeah.
as I said, we apply load and we measure the size of the dent and then we use it to find the BHN. Now, something I want you to notice is that the BHN has units, and the units is just the units of the force in kilogram divided by the units of the area in millimeter square. Okay, so kind of a pressure units. Now, the load, I know that some of you think that the load is constant, but kind of it's not. And so it looks like it depends on the hardness of the material. This table would tell you the amount of load that you should apply. So for example, if you're testing a very hard material like steel, then the load will be high, like 3,000 kilogram, but the duration, which is controlled by a stopwatch, so you have to turn the stopwatch on, it's only 15 seconds. While if you test a softer material like aluminum, you apply a smaller load like 500 kilogram, but you must leave it for 2 minutes. And I think it's not a matter of the load only, it's a matter of how much you leave the load. And that's why kind of those are equivalent effects. Whether you apply a bigger load for a shorter time or apply a smaller load for a longer time, they have the same effect. Now, so the first method to find the BHN is using the formula. Also on the machine, there is one table on the machine that allows you to find the BHN. Okay, so here is the machine and here is the chart. This chart right here, it allows you to find the BHN. I zoom in and I give you here a kind of a snap or zoom into to the chart. And I want everyone to look through this section of the chart. Okay. Now, how do we use this chart is simply like this. Number one, if we, for example, testing steel, and we know if we're testing steel, the load is 3,000 kilogram. And let's say I did the measurement, I measured the indentation diameter and it's 4.7 mil, okay? So how much is my BHN?
16.3.
It's
163.
It's 163, okay? So all you have, very simple, all you have to do is you go vertical, you go horizontal on the dent size, this will give you the BHN, which you will get the same number exactly if you use the equation. So two options, whether to use the chart or the equation, get the same results. However, in the lab, I'm very clear, I want you to use the equation because simply I did not give you the entire chart, only a section of it. Okay, I want to move now to the next machine, which is called Rockwell. In Rockwell, we do the same thing. We're trying to again apply load on one specimen, and then we kind of somehow, okay, so measure the size of the dent or the mark. The difference is here in Brinell, we're measuring the diameter of the dent. In Rockwell, we're not really measuring the diameter. In Rockwell, there is a scale. So this scale in the middle here, it measures the penetration itself, the penetration of the indentor into the surface of the metal. Okay? So I want you to understand that Brinell and Rockwell, both of them, they kind of work the same way, but the results will be based on different measures. One is based on the diameter of the dent, and the other one is based on how much this indentor went into the surface of the specimen. Now, also for the Rockwell, there is another detail, which is, okay, when we test harder material and we test softer material, are we using the same load? Are we using the same indentor? The answer is no. Watch this. So if you're testing a relatively hard material like steel, then what we do is we use diamond tip, which is very hard. We also use a load of 150 kilogram, and we read the reading on scale C. Okay, so number one, here is the diamond tip on the left. Here is how you set the load, which is from the side of the equipment. I'll go back here. You can see on the side here, there is a knob, and this knob allows you to change the load from 100 to 150 or the opposite. So for harder material, we change the indentor to be diamond tip. We adjust the load to 150, and then finally we read on scale C. Now, please everyone look through the gauge. The gauge has two scales, should be very clear. has a black scale called scale C and a red scale called B. If you see that, please give me confirmation. If you're able to see the scale, please give me the confirmation. Okay.
Yep.
Okay. So what happened is, as I said, if we're testing harder material like steel, number one, I use diamond indentor. Number two, I use 150 kilogram. Number three, I read on scale C. Now, when I read scale C, can anybody tell me the reading, which is very simple? So you can see that's the gauge and it's between 50 and 60. Can anybody tell me what is the reading on scale C?
52.75, roughly?
Yes, sir. Yes, sir, correct. 52.7. Okay, you don't have to be so accurate because I'm going to show you the chart. That chart doesn't have this much like small numbers. Okay, so 57 even is okay. So this number 57. Okay, so how about if you were to read on the same reading on scale B? How much? On scale B, on the red scale?
82, 80, 82,
Yeah, 0.7.
almost 83,
82.7.
82.7. Yeah.
Okay, so when do we read the red scale, the scale B? It's right here. Softer material. Remember, there are some harder material like steel, but there are some softer material like, for example, aluminum. Aluminum is soft. So if you test softer material, number one, you want to change the indentor to 1/16 of an inch diameter steel ball, not diamond tip anymore, which is right here. So this is your steel ball, 1/16 of an inch. This diameter is which is 1.5 mil. And then you adjust the load to 100 kilo. So here is the 100 kilogram load from the side of the equipment. Finally, when this machine when the indentor dives into the surface, we want to take the reading on scale B, which is the red scale. Now, one thing I want you to write it down, and it's here on my presentation, that unlike BHN, so the BHN, we know it's in kilogram per millimeter square, while Rockwell number has no units. The Rockwell hardness number has no units. And so this number here has no units. It's not in millimeter, it's not in centimeter. It's a number calibrated to give you the relative hardness of the materials. And I know right now some of you will ask, okay, so how can I relate if I tested the same material on Brinell and I got 82, or I tested the same material on Rockwell, I get different number. How those numbers are related? Watch this. So at the very end, there is one chart, and this chart here, it gives you the correlation between the different hardness tests. Let's get clean it first. You can see here we have Brinell. So this scale is the most left one is Brinell. This one is Rockwell B, and this one is Rockwell C. And there are some other Rockwell machine which is for softer material like plastic. We don't have them at SAIT, so I'm going to cross those ones called the scale Rockwell M and Rockwell R. Those are for softer material like plastic. In SAIT, we have Brinell, we have Rockwell B and C, which they are the same machine at a different scale. Now, for example, let's say you run the Brinell machine, you found the BHN, and the BHN happens to be 90. BHN happens to be 90. You can see here 90 on BHN, the Brinell, corresponds to roughly about 55 on Rockwell B. Okay, and this is for brass and aluminum, which means softer material. One more time, let's say you tested one specimen on Brinell and you got, let's say, 200. Okay, let's say go 200. So 200 corresponds to 90 on Rockwell B, corresponds to almost 12.5, let's say, on Rockwell C, and this is easily machine steel, like harder material. So some observation from this chart is the larger BHN, what does it tell you? The larger BHN or larger Rockwell B or larger Rockwell C, does it tell you the material is harder or softer?
Harder.
Harder. Look at the scale and you'll see on the very bottom plastic, huh? So plastic on the very bottom. Next is aluminum and copper. Next is easily machined, and then filing, and then cutting tools. Okay, so the larger the number is the harder the material. Okay. Now there is something, couple of things I want to mention before I end the recording and the lab is, now I'll go back to this slide here. And obviously on this slide, looks like I have done many tests on the same specimen. You can count the marks, huh? So 1, 2, 3, and so on. Now I have a simple question for you, okay? And the question is, do you think the location of these dents here, does it affect the results? In other words, should I go very close to each other? Like if I were to test many tests on the same specimen, I have one specimen, I'm making more and the dents on the same specimen. Can I go very close, or you think that affects the results, the accuracy of the results?
No, that'll affect it because the dent is going to be compressed from, so it's going to be it's going to be harder after there's a dent in the
Agree,
metal.
agree. The other question is, would you think I can go very close to the edge? Like if I show you the picture one more time, can I go very close to the edge? Like can I make my dent like right here?
No.
I think no.
Because simply if you go too close to the edge, there is no support material. It will give you a false indicator of the hardness. Now, so then when I make the test, what are the things that I need to pay attention to? One more thing before I show you the full list. The surface of the specimen, can it be uneven? Can it be uneven, or it has to be perfectly even and perpendicular to the surface to the indentor?
No, it has to be even.
And that's why those specimens, we have to make them, we have to machine them. We have to make sure that the surface is perfect, free of any dirt or grease. If you are wondering what is the full list of all those consideration, it's already available on D2L. So if you go back to D2L, and you will see file called worksheet. So on the worksheet right here, if you give it a reading, you will see number one is the condition of the indentor. So with time, what happens to these indentors? What happens to those ones? Okay, with time, what happened to this bone? It will wear over time, and this will affect the results. So the condition of the indentor. Number two is the accuracy of the applied load. You can see in Brinell, we have this machine, and this machine will tell us on this gauge here, will tell us the load is 3,000. Is it really 3,000 or maybe 2,900? So the accuracy of this gauge, and that's why these machines will have to be calibrated every some time. What else? Are we impacting the load? Like when I hit my specimen, is it really impact or static load? This will affect the results as well. The surface condition of the specimen, the thickness, even the thickness. Can we run this test on a very thin, very thin specimen? Like the thickness of the specimen, can it be very thin? No, you have to maintain one specific thickness. So that's why I'm asking all of you to spend some time right now, all of you, to read this page. The file is available on D2L, and the file name it's called, I'll show you the file name. The file name it's called under content. And right here it's called strength of material 246, lab 1 and 2, hardness worksheet. So if you open this file, you will see all those considerations to get accurate results. Now, last, before I let you go into the group, where after you do the reading for this lab, where can you find the quiz? Okay, right now I'm giving you clear direction on where you can find the quiz. I think I mentioned it before, but just in case. So for lab number 1, the quiz is under tests. Please write it down, under tests. So if you go under tests, you will see I have a folder here or category called lab quizzes, so not confused with ramen stuff. So ramen stuff is by itself. My stuff will be by itself, so not to confuse you. So here is lab number 1, lab number 2, and if you go preview or take the test, you will see what I did is I created a section, and you can see hardness test. That's lab number 1. And if you keep going down, you will see many of them, most of them are lab number 1. However, I think starting from question number 16, there is another test called Sharpie Impact. Sharpie Impact. In this lab, I will not cover lab number 2, which means you cannot submit. You cannot submit. However, you can simply answer these questions until number 15. And then in the next class, when I cover Sharpie Impact, you will just do, I think there's only 4 of them. I think, yeah, there is 4 of them, which you will answer next class. And remember, you can log in and get into this quiz and log out as much as you can, or as many times as you need, because at the end you need to save. When we finish lab number 2, we can submit. Is that clear? So today, when you do the reading and understand, you will answer question from 1 to 16. Next time, you will do only 4 questions, 17 through 20, and you'll be able to submit. Now, after, I can give you a break 5 or 10 minutes, and then you can go to your, I already built the groups, so you find yourself in one specific group. You can meet into the group, you can go through the questions. However, I want to say something. I designed my lab so every individual student will have some random numbers. So for example, Russell numbers will be slightly different from, let's say, Masoud. So I mean, you cannot compare the numbers because I use random generator, so which will make every student unique from the other. Okay? You guys following?
Yep.
Any question?
For the labs, where do we get the data from?
It's in the quiz. So in the quiz, there is a generator, and will generate for you the D. We'll give you the D in the lab.
Okay, so it's in the quiz part.
And let's make it clear. Let's make it clear. As I said, and hopefully now it's clearer. There are 2 ways. The old way, it's a report, which I give you the data. If we go D2L, the D2L will give you the data. Any question for me? Okay, so you guys can leave right now this channel. Leave it. When you come back after 5 or 10 minutes, whatever break you want to do, is come back to your channel. This channel is completely for you. It's private channel. I will not watch it. You can chat internally. You can meet with videos. It's all up to you. I would recommend you to work in groups because soon or later you're going to go back to school, so you need to know each other better than now. Any question before we give you a break? Okay, there is something in the chat. Somebody's shy. Slide 4 has it, but not slide 6. Raver, can you please tell me what do you mean?
It's talking about the formula that I mentioned in the middle.
Okay. Thank you so much. Thank you so much. Okay, so guys, I will leave, and probably I'll come back to you and ask you if you have any question within the group. Okay, thank you.